get it going. So, as always, can I get a acknowledgement in the chat to let me know you guys can hear me? Awesome. All right, so let's see. Welcome to Wednesday, and welcome to the last day of our regular class, right? So this is the last lecture. After today is just review for exam, take an exam, review some more for another exam, take that exam. So this is the last lecture, the last lesson of the class. So congratulations on making it this far. So are there any questions, comments, or concerns before we get started? All right, so I made a review, like a Quizlet flashcard deck. It's posted up on Blackboard. It's also posted up somewhere in this chat thread. Go and find it. We'll use that to do our review on Friday. And then, of course, you got to stick with those. I made those flashcards at the same time I was writing the exam, so it's, basically what I'm saying is study the flashcards. If you feel good about those flashcards, you're probably going to do just fine on the exam. So, any questions about that? Yep. Oh, yeah, it's definitely going to go away when the test opens. Yeah. So, keep that in your brain when you're studying. Yeah, so don't count on just having the flashcards open in another tab, because I'm going to take the flashcards down when the test opens. So, yeah, good question. All right, any other questions about that? All right, so let's go ahead. Oh, Edward's got more to say, man. Never mind. All right, so let's talk about state tables and graphs. So we're going to kind of take today and we're going to go through two examples of sequential circuits and look at how we can derive what we call a state graph from those circuits. So transition tables. We've already seen transition tables for small sequential circuits, but to design larger sequential circuits, we need a more systematic approach. So what we're going to have is the transition and state tables for a sequential circuit specify the next state and the output of the circuit in terms of the present state and the input. So we're going to use this method to construct a transition table and then eventually construct a state graph. So as we work through each of the steps, we're going to use this circuit as an example. So we're going to kind of build off of this circuit sort of one step at a time. So step one is determine the flip-flop input equations and the output equations for the circuit. So what that means is we need to know why my pin doesn't work. Let's see, pin, what dA is, dB, and Z. So looking at dA first, we see that dA is equal to X XOR B prime. And dB, so that's an XOR gate, that's got me tripped up in the last class, is an OR gate, so dB is equal to X or A. And then finally Z is just equal to, so we have an XOR gate tied to B and A, so Z is equal to A XOR B. Cool? All right, any questions about step one? So you look at the circuit, you figure out, well, what are the Boolean expressions for the output and for the flip-flop inputs? All right, step two, derive the next state equation for each flip-flop from its input equations using one of these relationships. So before I think last class we saw an example of the relationship for a JK flip-flop. So what we need to do is go and look and see, well, what are we working with? Here we're working with D flip-flops. So we're going to go and say, all right, well, that's what we got. So Q plus equals D. So what that means is that A plus is just equal to directly dA, and B plus is equal to dB. These are transparent flip-flops. But of course, for T or SR or JK flip-flops, it's going to be a little bit more sophisticated. So yeah, so let's say that, so we've got A plus is equal to dA, which is equal to x or b prime. Now, for the next step, what we need to do, well, I'll take that back. We'll get to that in a second. And then b plus is equal to db, which is equal to x or a. All right. So the next step, step 3, is we're going to plot those equations onto K-map. So let's look at A. So remember, A plus was equal to dA, which was equal to what? X or b prime. Well, what we're going to need is a product of sums equation for this. So we're going to need A plus is equal to x and b prime prime, or x prime and b prime. We can simplify that one more step. Let's see. Liam says, can you reliably identify flip-flops just by looking at what inputs are labeled as, or might you change the input names on the test? No, they're going to be labeled directly. I'm not going to label a JK flip-flop with Ds. So yeah, so whatever the input is will be pretty straight up. If it's S and R, it'll be S and R. If it's JK, it'll be JK. I'm not going to try to trick you on the test. Because without the labels, you wouldn't be able to tell the difference between some of them. All right, so A plus is equal to x and b, or x prime and b prime, and that's what we're going to see here on, use a different color, on the K-map for A plus. So we've got what? We've got xb, so x is equal to 1 and b is equal to 1. So that's this grouping right here. And then x prime b prime is x is 0, b is 0, which is going to be that group right there, just like that. So just like we've seen before, we're kind of reverse engineering the K-map based on our equations. And we'll do the same thing for b plus, right? B plus was equal to x or a, right? So that's already in product of sums. So the term just x is going to be this column. And the term for A is going to be this box at A equals 1. So that's how we reassemble the K-map from our equations. Any questions about that? All right, step 4, combine these maps to form the transition table. So we've got a table here. We've got the present state. And notice here that it's listed out in gray code, 0, 1, 3, and 2. And that's by design. That's because we want it to match up with the columns of our K-map. So if you look here, so we've got AB is 0, 0, 0, 1, 1, 1, 1, 0. And then we have our next state, right? A plus B plus. For x equals 0, for the A plus part, we look over here at A plus for x equals 0, and that's 1, 0, 0, 1, right? And that's what we have here, 1, 0, 0, 1. And then for B plus at x equals 0, we look over here at the B plus map, and we've got 0, 0, 1, 1. And that's what we have, 0, 0, 1, 1. And then we do the same thing for x equals 1. For A plus, we look over at the x equals 1 column, 0, 1, 1, 0, and that's what we get, 0, 1, 1, 0. And then for the B column, we look again at x equals 1, and we get 1, 1, 1, 1. And that's what we have. And then finally, remember that z was equal to what? A, x, or b. Right? So that's going to look here. So 0, 0 XOR 0 is 0, 0 XOR 1 is 1, 1 XOR 1 is 0, and 1 XOR 0 is 1. So that's what we have there in the output column. All right. Any questions about how we do that? You just take the columns of the K-map directly as they are and list them out. So finally, the last step, or the second to last step, is a state table is a transition table, but we've taken the binary notation and we've replaced it with what we call these state labels. So if I go back to the previous one, I'm gonna list, despite the fact that they're in gray code, I'm still gonna list them as state 0, state 1, state 2, state 3. And these labels are primarily arbitrary. Like I could, let me change that to yellow, right? I could say that this is state, A, and state B, and state C, and state D, right? I'm just applying some labels to each of these states one at a time. And so what happens then is you look at it and say, all right, well, given my, present state, my inputs, well, what are my next states going to be? So if 1, 0 is state 3, that means that's state 3, that's state 0, that's state 1, and that's state 2. And then over here we have state 1 and state 2 and state 2 again and state 1. And then output has no state, so it's not really a thing. But what we're doing is taking that and just mapping these things over, right? So if I'm at state 0 and I get an input of 0, then I go to state 3. If I'm at state 2 and I get an input of 1, well, then I stay at state 2. So we're sort of taking the binary out and we've just focused on labeling what state we're going to go to. And then, of course, output always stays the same. Any questions about the state table? All right, this is going to go pretty quick. So finally, we've got the state graph. The state graph contains all of the same information as the state table. It's just done in a graphical form. And for this machine, right, a Moore machine where the present output is only dependent on the state, this is what it looks like. So I'm going to label this actually as a Moore state graph. And so I've got circles for each of my states, state 0, state 1, state 2, state 3. And on the inside here is going to be whatever the output is. Whatever my Z is. And then we'll see transition arrows. So from state 0 here to state 1, and then from state 1 back to state 0. And those are the inputs. So here, if I'm at state 3, and I get a 1, well, here I can see that a 1 takes me to state 1. But if I'm at state 3 and I get a 0, well, that takes me to state 2. So you can see that's reflected here. If I'm at state 3 and I get a 0, I go to state 2. And if I'm at state 3 and I get a 1, I go to state 1. And of course, my output at state 3 is a 1. So hopefully you see that, and that makes a lot of sense. Like I said, it's the same information that's in the state table. It's just in a graphical form. And a lot of people find this kind of easier to visualize the behavior of the state machine by looking at it this way. Any questions about the state graph? All right, so now let's go ahead and take a look at one more example, and we'll look at this Mealy machine circuit. And we'll work through the same steps, but just with this one. So a couple of things to notice right off the bat are we're using JK flip-flops, and then it's a Mealy machine, which means it's got this sort of big old output circuit that's also dependent on the input. So step 1, determine the flip-flop input equations and the output equations. So here each flip-flop is going to have two equations, one for J and one for K. So we've got what? J A is equal to X and B, and Ka is equal to X, and JB is equal to X, and KB is equal to X and A. And then down here we can see that Z is equal to X and B prime, or X and A, or X prime and A prime and B. So there we go. We've derived our flip-flop input equations from looking at the circuit. Are there any questions about this step? All right, so next up, derive the next state equation for each flip-flop from its input equations using one of the following relations. Now we're looking at JK flip-flops, which means that we're going to go with that set of equations. Let me write out some of the stuff again. I've got JA equals what? XB. KA equals X. I've got JB equals X. And I've got KB equals XA. All right. So now I need, let's see, an equation for A prime. A prime is going to be, excuse me, A plus is going to be JA and A prime, or KA prime and A, which is going to give me, let's see, JA is equal to XB, so that's going to be X, B, and A prime, or KA is X, so that's going to be X prime and A. So there we go. That works out pretty nicely. Let's see. Now we've got B plus, which is going to be now JB and B prime, or KB prime and B. And let's see, JB is equal to X, so that's going to be X and B prime, or KB is equal to XA, so that's going to be X, A, all of that prime, and B. Remember that we need to get everything into product of sums form. I'm going to go up here and rearrange A plus real quick to just be sort of in a nice alphabetical form. X, A, B, or X prime and A. And then down here, B plus, it's going to be what? X, B prime, or we're going to apply De Morgan's theorem. Look here, even in the last lesson, we've got some De Morgan's theorem. X prime or A prime and B, and we need to simplify that down to one more step. We're going to have X, B prime still, or X prime B, or A prime B. So let's see, there's our characteristic equation for flip-flop A, and here's our characteristic equation for flip-flop B. Just like that. All right, so any questions about how we derived these equations? All right, step 3, plot each of these on a map. So let me go ahead and write these equations out one more time. I got A plus is equal to XAB, or X prime A, I've got B plus is equal to this whole big long thing. B plus is equal to X prime B, or X B prime, or A prime B. And then I've got an equation here for Z, which was, gotta go way back, X prime B, XA, X prime B, or XA, or X prime A prime B. X prime A prime B. All right. So now we're ready to go ahead and set up our next, our transition table. So let me do that. I'm going to kind of lay it out over here while we've got everything happening. Let's see. We got X. Well, we got to plot the stuff on the map first. I kind of skipped a step. X, A, and B here on the A+. That's going to be X is 1, A is 1, B is 1. Ooh. Did we make a mistake somewhere? We must have. Let's see. Let's go back and take a look. Ah, that's because it's JA. Yep, you're absolutely right, Megan. Good job. So it's J and A prime, which means that should be A prime, which means that should be A prime. It's always good to get the answers there. So that's XA prime. So that's X is 1, A is 0, B is 1. So that's this term here. And then finally, X prime A is X is 0, A is 1. There we go, just like that. And for the B plus, X prime and B is X is 0, B is 1. So that's going to be this guy. Then X and B prime is going to be X is 1, B is 0. So that's going to be these guys on the outside. And finally, A prime B is going to be A is 0, B is 1, which would be that group. And then for Z, we got X prime and B, so X is 0, B is 1. Let's see. Did we make a mistake here too? Let's see. X prime and B. Which would give me a 1 there. So let's go back and take a look at Z. Oh, it's because it's X and B prime, not X prime and B. X and B prime. X and A. All right. So there we go. X is 1, B is 0. That makes a little bit more sense. That's this guy. Then X and A is X is 1, A is 1. Oh my goodness, did we screw it up again? No, I didn't. It's these guys. There we go. And then X prime, A prime, B. X is 0, A is 0, B is 0. There is no homework for this one, Liam. This one's for free. Just a test. All right. So now let's go ahead and lay out. Everyone immediately logs out of the chat. No homework, I don't care. But it's going to be on the test on Monday. So let's go ahead and lay out our transition table before we look at it on the next slide. So A and B is going to give us 0, 0, 0, 1, 1, 1, 1, 0. And then we're going to have our next state, our A plus, B plus. First for X equals 0. And for X equals 1. So for X equals 0, it's going to be 0, 0, 1, 1. 0, 0, 1, 1. And for B, it's going to be 0, 1, 1, 0. 1, 0. And then for X equals 1, the A column is going to be 0, 1, 0, 0. And for B, it's going to be 1, 1, 0, 1. And then over here, I'll put the Z's. So we got our Z's. Now remember, it's a Mealy machine, which means it's also dependent on the input. So I'm going to have a different Z for X equals 0 and a different Z for X equals 1. So for X equals 0, I'm going to get 0, 1, 0, 0. And for X equals 1, I'm going to get 1, 0, 1, 1. So there we go. Any questions about how we derived this table? All right, so here we go. This is the table we just looked at. And you can see it matches up, right? 0, 1, 3, 2, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, and then 1, 1, 0, 1. Come back over here, 0, 1, 0, 0, 1, 1, 0, 1. It all matches up. And then Z was what? 0, 1, 0, 0, 0, 1, 0, 0, and 1, 0, 1, 1 is 1, 0, 1, 1. So the next step is we need to take this and make our state table. So I'm going to go ahead and label these guys. State 0, state 1, state 2, state 3, which means here I've got, what, state 0, state 1, state 2. So that means it doesn't change at all if x is equal to 0. And then here I've got, what, state 1, state 2, state 0, and state 1. So if I go and look at my table, that's what we've got here. So if x is equal to 0, the next state is equal to the present state. And if next state is equal to 1, then it progresses from 0 to 1, 1 to 2, then 2 back to 0. Notice that it never progresses to state 3. And then we have some output dependent on our input. Yes, it's mine. This will be available on Blackboard. So the last step is to take this and make our state table. Now notice, our state graph. Notice that it's a little bit different than the one we saw before. So this is a Mealy machine state graph. So we've got our states just inside the bubbles by themselves. And then here we have on the top line, that's our input. And then here we have our output. So here at state 0, if we're at state 0, if we get an input of 1, then we're going to go to state 1, and we're going to produce an output of 1. So notice we kind of go around the cycle. If it's at 0, it always stays the same, and then it only sort of progresses if the input is equal to 1. Notice that if we start, the only time to get to state 3 is if we start at state 3, and if we are at 0, then we'll just stay at state 3 forever, and then if we go to 1, then we get sucked into the big loop that goes from state 1 to 2 to 0 to 1 to 2 to 0, back and forth again. And let's see, it looks like it only produces, no, that seems kind of arbitrary. Okay, any questions about drawing that state graph? All right, in that case, let's just recap real fast the procedure. Step 1, determine the flip-flop input equations and the output equations from the circuit. Step 2, derive the next state equation for each flip-flop from its input equation using the correct flip-flop relation equation. So see what flip-flop you're working with, find the correct equation. Step 3, plot the next state map for each flip-flop. So take those equations, create the k-maps for each one. Step 4, combine those k-maps into the transition table, right? Just chop those columns. Step 5, derive the state table from the transition table, which is to say just make the labels for all the states. And then step 6, draw the state graph from the state table. All right. Any questions about that procedure? Cool. Well, in that case, that is it, man. So if there are no more questions, comments, concerns, on Friday we will sort of take that Quizlet deck and work through the review. Like I said, focus on that deck as you're studying for the exam. That exam, of course, will be on Monday. It'll be available all day from midnight to midnight, all day on Monday. So, any last questions, comments, concerns? I see Edward typing something. I don't know who Arian is, but Ari is probably available. Megan asks, what chapters will be on the test? This will be basically chapters 11, 12, and 13. You're welcome. All right. If there is nothing else, then thank you for joining me today. Like I said, that's the last lesson of the entire course. You've reached the end. The only thing left to do is take some exams. So I'll see you guys on Friday, where we will review for the third and final midterm exam. Thank you. See you guys on Friday. You too. Bye.